we consider the function f of x equals to x squared. It is a function that sends real numbers to real numbers. Let's visualize it. Here we have the domain of the function, which is a real line on the left, and the codomain, which is again a real life on the right. Let's see the image of one element in the domain. We have the element given by the number 2.72. Its image will be the square of it, so 7.4, in the codomain f, and we have drawn an arrow going from the element in the domain to the element in the codomain. Now this is just an image of one element in the domain. There are infinitely many of them on which f acts. So let's see a few more of them to have an idea what the image of f might be. Okay, so now we have the image of about 20 different elements in the domain, chosen randomly. So as you can see, all the images are concentrated in the positive half line of the codomain, so they're all greater or equal than 0. Of course, we know that the image of f of x equal to x squared cannot be negative, and in fact it is surjective on the subset of the real numbers given by non-negative real numbers. Therefore, from this picture we can see that the image, at least we have an evidence that the image of the function f is precisely what is marked here in purple with the purple line, so non-negative real numbers in the codomain of f. Now, next step is to start to draw the graph of f from this situation where the domain and codomain are disjoint one to the other and they are connected by arrows indicating the action of the function f on a finite number of elements in the domain. We cannot really extend much more than that because we cannot show the image of infinitely many or even finitely many, but in such a high number that the picture will not be understandable anymore. Therefore, let's slowly go through the representation of f through its graph. Remember that its graph is a subset, the graph of a function is a subset of the Cartesian product of the domain times the codomain. So let's first construct this Cartesian product. What happened here is that we rotated the domain that was vertical, just parallel to the codomain, in order to intersect it with the codomain. So now we have two orthogonal axes, and this is the typical way in which we represent r squared. Therefore, every point we see here in this image is representing an element in the Cartesian product of domain times the codomain, and inside this picture we are going now to highlight a few of the points in the graph of the function f. Let's start with 6 of them. In here we see the construction, the explicit construction of the point in the graph starting from an element in the domain and its image in the codomain. We see here the element 1, 0 in the domain, whose image is again 1.0, and the element in the graph corresponding to this pair of numbers is precisely the point of coordinates 1, 1. Therefore it is this. And the second one is -2, its squared is 4. So we are looking at the point in the graph right here. And so on, 3, its image is 9, so we are looking at this point right here. Then -2.5, its square is 6.2, therefore we are here. Let's see if we draw a certain number of points in the graph, randomly picked, about a few hundreds of them at least. Okay, we have an idea now exactly of what the graph of f looks like. We see that the shape of this graph is what is normally known as a parabola, and this is exactly as expected. So we know, and we have learned in high school, that this is exactly what happens, but we actually constructed it as a pointwise determination of the graph of f. Let's see now, if we pick a point in the graph, how we can recover the element in the domain whose associated point in the graph is the one we are starting from. So essentially we're going to describe what the map I is, the map I that factors the map f through the graph that we discussed in the previous lecture. So we start with the yellow point here. Now, if we project it down to x, we hit the x-axis in the, well, in this case we are just representing exactly the point that we started from a few minutes ago in the domain. You remember the first point we considered on which the f acted was exactly the element in the domain given by the number 2.72. So this yellow dot is the point in the graph associated to it. So if we start from that, we can recover the element that is associated to it, just projecting it down to the domain. And so when we hit the domain, we hit it in a specific number, and the yellow dot will be given by, in the graph, will be given by the pair in which 2.72 is the first coefficient, and the second coefficient will be the image of f of 2.72, therefore the square of 2.72. So projecting on the y-axis, we see the image of 2.72, which is 7.4, and the pair 272 7.4 gives exactly the point we started from in the graph of f. This is a description of the map I over about 20 different elements in the domain. So the map I sends elements in the domain to the corresponding elements in the graph, just in a sense lifting it up until it hits the graph. So it has to go as high as the image of the point we are starting from in the codomain. Let's see now the map Q, which goes from the graph to the codomain, for which the composition I composed with Q is exactly f. So it is a factorization of f. It's simply the projection of the points in the graph on the vertical, on the codomain, the vertical axis.